at satellite imagery and they realize, oh my God, that's the caldera of a volcano, like this Yellowstone thing. We thought it was just this crazy place with hot springs. Like, no, that's a super volcano that is a continent killer.
In Wyoming lies a dormant volcano that has kept scientists and geologists on their toes for decades, a typical sleeping giant. This landmark is responsible for one of the most catastrophic events in recorded events. In recent times, the Yellowstone region experienced a series of hundreds of earthquakes, a phenomenon documented by park officials. Should we be concerned about the possibility of another significant earthquake?
These are the steep hillsides giving way to the force of water.
Whoa.
And the massive boulders narrowly missing cars on the road.
Join us as we investigate the recent seismic activity in Yellowstone as recorded by park authorities and explore the effects of these events. The very first national park of the United States, Yellowstone, is located in the northwest corner of Wyoming. It is the first national park in the United States. This large park, which extends into Idaho and Montana, is well known for its wildlife and many geothermal features. This park also boasts a wide range of biomes, rock ranges, and forest ecoregions, among many other regions. Going back, Native Americans have inhabited the Yellowstone region for at least 11,000 years. However, organized exploration of this region did not officially begin until the late 1860s. On the surface, this region is a tranquil environment, but then never judge a book by its cover. Yellowstone is home to 10,000 hydrothermal features, including geysers, hot springs, and fumaroles, making it the largest concentration of such on Earth. Beneath the terrors of Yellowstone are the breathtaking landscapes that sit atop. It is a geological marvel that has somehow kept scientists and visitors awestruck. This vast wilderness expands to over 2.2 million acres of land, and it is just the perfect place to take pictures for a family vacation. It is a testament to the raw power of our planet Earth, and it always serves as a way to study the Earth's inner workings. At the heart of its allure is the Yellow Caldera. The Yellowstone Caldera is the largest volcanic system in North America, and worldwide it is only rivaled by the Lake Toba caldera on Sumatra. It has been termed a supervolcano because the caldera was formed by exceptionally large, explosive eruptions. The magma chamber that lies under Yellowstone is estimated to be a single connected chamber, about 37 miles long, 18 miles wide, and 3 to 7 miles deep. The current caldera was created by a cataclysmic eruption that occurred 640,000 years ago, which released more than 240 cubic miles of ash, rock, and pyroclastic materials. This eruption was more than 1,000 times larger than the 1980 eruption of Mount St. Helens. It produced a caldera nearly 1 kilometer deep and 45 by 28 miles in area and deposited the Lava Creek Tuff, a welded, tough geologic formation. The most violent known eruption, which occurred 2.1 million years ago, ejected 588 cubic miles of volcanic material and created the rock formation known as the Huckleberry Ridge Tuff and the Island Park Caldera. A smaller eruption ejected 67 cubic miles of material 1.3 million years ago, forming the Henry's Fork Caldera and depositing the Mesa Falls Tuff. Each of the 3 climatic eruptions released vast amounts of ash that blanketed much of central North America, falling many hundreds of miles away. The amount of ash and gases released into the atmosphere probably caused significant impacts on world weather patterns and led to the extinction of some species, primarily in North America. With the magnitude of each eruption, one cannot help but wonder what would happen if such eruptions occurred today. What interests scientists the most is the increase in seismic activity recently within the park, with hundreds of earthquakes occurring in a matter of days. This has sparked multiple discussions about a future eruption. The scientist in charge of Yellowstone has stated that the region is experiencing a swarm of activities from time to time. A 3-month swarm of 2,400 earthquakes occurred between June and September of 2017, with some even getting as high as 4.4 magnitude. This has caused scientists to start monitoring the situation with bated breath, as concerns are mounting amongst the public and experts alike. At the heart of this concern is the elephant in the room, the caldera. The chances of a catastrophic eruption are considered low. However, that does not mean that the recent seismic activities have gone unnoticed. These activities observed in the region have brought about a much closer scrutiny of the region's geological stability. The source of the Yellowstone hotspot is controversial. Some geoscientists hypothesize that the Yellowstone hotspot is the effect of an interaction between local conditions in the lithosphere and upper mantle convection. Others suggest an origin in the deep mantle. Part of the controversy is the relatively sudden appearance of the hotspot in the geologic record. Additionally, the Columbia basalt flows appeared at the same approximate time in the same place, prompting speculation that they share a common origin. As the Yellowstone hotspot traveled to the east and north, the Columbia disturbance moved northward and eventually subsided. An alternate theory to the mantle-plume model was proposed in 2018. It is suggested that the volcanism may be caused by upwellings from the lower mantle resulting from water-rich fragments of the Farallon Plate descending from the Cascadia subduction region, sheared off at a subducted spreading rift. Others suggest that the mantle plume could not have been a dominant force in Yellowstone volcanism due to the sinking Farallon Plate, as it acts as a buffer that breaks apart the plume. Any heat from the plume that does make it to the surface is limited. The volcanic history of the region provides valuable insights into its behavior, and this makes it a little bit easier to predict the timing of a future eruption. But as we know, predictions are not always totally correct. While seismic monitoring and geospatial analysis offer valuable tools for tracking changes beneath the Earth's surface, the complex interplay of geological forces makes accurate forecasting a formidable challenge. Yellowstone's numerous and diverse geothermal features, while fascinating subjects of study, also present their own set of challenges. Mud pools, for instance, are captivating but can be quite troublesome when they spew mud onto solar panels, instruments, and trail camera lenses. This mud can disrupt instrument operation, requiring frequent cleaning and maintenance. Emissions of acid gases like hydrogen sulfide from geothermal features can also corrode the metal components of equipment, which is a constant concern for researchers relying on these instruments for long-term data collection. Weather conditions in the park add another layer of complexity to scientific research. The heavy winter snowfall typical of the region can crush delicate instruments and cover solar panels, disrupting power supply and data collection. Batteries, essential for powering field equipment, are also susceptible to freezing in the park's frigid winter temperatures. Summertime spikes can bring down not only individual instruments, but also the radio repeaters needed for real-time communication of monitoring data. Deploying instruments in the backcountry of Yellowstone requires immense effort. Researchers often embark on strenuous hikes, carrying heavy loads over rugged terrain to reach remote locations. This physically demanding task is essential for setting up and maintaining equipment in areas that are key to different types of research and monitoring. The effort and time invested in these deployments reflect the commitment of scientists working in this unique environment. In December 2008, continuing into January 2009, more than 500 quakes were detected under the northwest end of Yellowstone Lake over 7 days, with the largest registering a magnitude of 3.9. Another swarm started in January 2010, after the Haiti earthquake and before the Chile earthquake. With 1,620 small earthquakes between January 17, 2010 and February 1, 2010, this swarm was the second largest ever recorded in the Yellowstone caldera. The largest of these shocks was a magnitude 3.8 that occurred on January 21, 2010. This swarm subsided to background levels by February 21st. On March 30, 2014, a magnitude 4.8 earthquake struck Yellowstone, the largest recorded there since February 1980. In February 2018, more than 300 earthquakes occurred, with the largest being a magnitude 2.9. The Yellowstone National Park region has experienced 3 massive eruptions in Earth's history. The biggest of these major caldera-forming eruptions occurred 2.1 million years ago and resulted in 2,150 cubic kilometers of material ejected, earning it supervolcano status. If another Yellowstone eruption were to occur today, what would happen? The devastating consequences. If the Yellowstone erupted today, if the Yellowstone supervolcano were to erupt, it would happen like this. Heat rising from deep within the planet's core would begin to melt the molten rock just below the ground's surface. That would create a mixture of magma, rocks, vapor, carbon dioxide, and other gases. As the mix amassed and rose over thousands of years, the pressure eventually would push the ground up into a dome shape and create cracks along the edges. When that pressure is released through the cracks, the dissolved gases would explode, emptying the magma in a quick fashion across the park. The eruption would entail more than dangerous lava flows and could be expected to claim as many as 90,000 lives immediately, and spread a 10-foot layer of molten ash as far as 1,000 miles from the park. Rescuers probably would have a tough time getting in there. The ash would block off all points of entry from the ground, and the spread of ash and gases into the atmosphere would stop most air travel, just as it did when a much smaller volcano erupted in Iceland in 2010. Equally as frightening is the nuclear winter that some experts say could blanket the US and other parts of the world if Yellowstone were to blow. Sulfuric gases released from the volcano would spring into the atmosphere and mix with the planet's water vapor. The haze of gas that could drape the country wouldn't just dim the sunlight, it also would cool temperatures. Falling temperatures would do a number on our food supply, decimating crops and throwing the food chain out of whack by leaving those at the bottom with little to eat. That's what many climate scientists believe happened in 535 CE after a supervolcano erupted in Java. Yellowstone last erupted about 640,000 years ago, and the United States Geological Survey says the probability that it will blow its top again is about 0.014% each year. According to the U.S. Geological Survey, the magma chamber beneath the Yellowstone caldera, the ground deformation resulting from previous volcanic activity, is only 5 to 15% molten, meaning there may not be enough lava flow for more explosive eruptions to occur. Whilst the Yellowstone caldera has a lot of scientists on their toes, what about the other supervolcanoes? Eruptions surrounding the state of California, the known volcanic history of the Long Valley. Caldera area started a few million years ago when magma began to collect several miles below the surface. Volcanic activity became concentrated in the vicinity of the present site of Long Valley caldera 3.1 to 2.5 million years ago, with eruptions of rhyodacite, followed by high silica rhyolite from 2.1 to 0.8 million years ago. After some time, a cluster of mostly rhyolitic volcanoes formed in the area. All told, about 1,500 square miles were covered by lava. All but one of these volcanoes, 1 to 2 million-year-old Glass Mountain, 264 were destroyed by the major eruption of the area 760,000 years ago, which released 600 cubic kilometers of material from vents just inside the margin of the caldera. Another lobe moved west over the crest of the Sierra Nevada and into the drainage of the San Joaquin River. The rest of the pyroclastic material, along with 300 kilometers of other matter, was blown as far as 25 miles into the air, where winds distributed it as far away as eastern Nebraska and Kansas. The eruption initially produced a caldera 2 to 3 kilometers deep. However, much of the ejecta went straight up, fell, and filled the initial caldera about 2/3 full. The caldera is a giant bowl-shaped depression, approximately 20 miles long, surrounded by mountains except to the southeast. The elevation of the bottom of the bowl ranges from 6,500 to 8,500 feet, being higher in the west. Near the center of the bowl, there is a resurgent dome formed by magmatic uplift. The southeastern slope from the caldera down towards Bishop, California, is filled with Bishop Tuff, solidified ash that was ejected during the eruption that created the caldera. The Bishop Tuff is thousands of feet thick and is cut by the Owens River Gorge, formed during the Pleistocene, when the caldera filled with water and overtopped its rim. The rim of the caldera is formed from pre-existing rock, rising about 3,000 feet above the caldera floor. However, the eastern rim is lower, only about 500 feet. Mammoth Mountain is a lava dome complex west of the structural rim of the caldera, consisting of about 12 rhyolite and dacite overlapping domes. These domes formed in a long series of eruptions from 110,000 to 57,000 years ago, building a volcano that reaches 11,000 feet in elevation. The Mono Inyo craters are a 25-mile-long volcanic chain situated along a narrow, north-south trending fissure system, extending along the western rim of the caldera from Mammoth Mountain to the north shore of Mono Lake. The Mono Inyo craters erupted from 40,000 to 600 years ago, from a magma source separate from the Long Valley caldera. The caldera has an extensive hydrothermal system. Casa Diablo Hot Springs at the base of the resurgent dome hosts a geothermal power plant. Hot Creek cuts into part of the resurgent dome and passes through Hot Springs. The warm water of Hot Creek supports many trout and is used at the Hot Creek Fish Hatchery. The creek was closed to swimming in 2006 after geothermal activity in the area increased. There are several other hot springs in the area, some of which are open to bathers. The tectonic causes of the Long Valley volcanism are still largely unexplained and are therefore a matter of much ongoing research. Long Valley is not above a hotspot, such as those which fuel Yellowstone caldera or the volcanoes of Hawaii, nor is it the result of subduction, such as that which produces the volcanic eruptions of the Cascades. The known volcanic history of the Long Valley caldera area started a few million years ago when magma began to collect several miles below the surface. Volcanic activity became concentrated in the vicinity of the present site of Long Valley caldera 3.1 to 2.5 million years ago, with eruptions of rhyodacite, followed by high silica rhyolite from 2.1 to 0.8 million years ago. After some time, a cluster of mostly rhyolitic volcanoes formed in the area. All in all, about 1,500 square miles were covered by lava. All but one of these volcanoes, 1 to 2 million-year-old glass mountain made of obsidian, were destroyed by the major volcanic explosivity index eruption of the area 760,000 years ago, which released 600 cubic kilometers of material from vents just inside the margin of the caldera. The 1980 Mount St. Helens eruption was an eruption releasing 1.2 kilometers. About half of this material was ejected in a series of pyroclastic flows of a very hot mixture of noxious gas, pumice, and volcanic ash that covered the surrounding area hundreds of feet deep. One lobe of this material moved south into Owens Valley, past present-day Big Pine, California. Another lobe moved west over the crest of the Sierra Nevada and into the drainage of the San Joaquin River. The rest of the pyroclastic material, along with 300 kilometers of other matter, was blown as far as 25 miles into the air, where winds distributed it as far away as eastern Nebraska and Kansas. In May 1980, a strong earthquake swarm that included 4 Richter magnitude 6 earthquakes struck the southern margin of the Long Valley caldera. It was associated with a 10-inch dome-shaped uplift of the caldera floor. These events marked the onset of the latest period of caldera unrest that is ongoing. This ongoing unrest includes recurring earthquake swarms and continued dome-shaped uplift of the central section of the caldera, accompanied by changes in thermal springs and gas emissions. After the quake, a secondary access road was created as a potential escape route for the town of Mammoth Lakes. Its name was first proposed as the Mammoth Escape Route, but was changed to the Mammoth Scenic Loop after Mammoth area businesses and landowners complained. In 1982, the United States Geological Survey under the Volcano Hazards Program began an intensive effort to monitor and study geologic unrest in Long Valley Caldera. The Long Valley Caldera hosts an active hydrothermal system that includes hot springs, fumaroles, steam vents, and mineral deposits. Hot springs exist primarily in the eastern half of the caldera, where land surface elevations are relatively low. Fumaroles exist primarily in the western half, where elevations are higher. Mineral deposits from thermal activity are found on an uplifted area called the Resurgent Dome, at Little Hot Creek Springs, Hot Creek Gorge, and other locations in the south and east moats of the caldera. In hydrothermal systems, the circulation of groundwater is driven by a combination of topography and heat sources. In Long Valley Caldera, the system is recharged primarily from snowmelt in the highlands around the western and southern rims of the caldera. Studies and analysis may indicate that the greater hazard comes from hydrothermal activity, which occurs independently of volcanic activity. Over 20 large craters have been produced in the past 14,000 years, resulting in such features as Mary Bay, Turbid Lake, and Indian Pond, which was created in an eruption about 1300 BC. In a 2003 report, USGS researchers proposed that an earthquake may have displaced more than 77 million cubic feet of water in Yellowstone Lake, creating colossal waves that unsealed a capped geothermal system and led to the hydrothermal explosion that formed Mary Bay. Further research shows that very distant earthquakes reach and have effects upon the activities at Yellowstone, such as the 1992 7.3 magnitude Landers earthquake in California's Mojave Desert that triggered a swarm of quakes from more than 800 miles away, and the 2002 7.9 magnitude Denali Fault earthquake 2,000 miles away in Alaska that altered the activity of many geysers and hot springs for several months afterward. Hot Creek has been a popular swimming hole for decades. Over a dozen people have lost their lives in Hot Creek since the late 1960s. But most of these happened to people who ignored the numerous warning signs and attempted to use the hydrothermal pools as hot tubs. The goal is to provide residents and civil authorities with reliable information on the nature of the potential hazards posed by this unrest and timely warning of an impending volcanic eruption should it develop. Most, perhaps all, volcanic eruptions are preceded and accompanied by geophysical and geochemical changes in the volcanic system. Common precursory indicators of volcanic activity include increased seismicity, ground deformation, and variations in the nature and rate of gas emissions. The eruption initially produced a caldera 2 to 3 meters deep. However, much of the ejecta went straight up, fell, and filled the initial caldera about 2/3 full. One of the largest supervolcanoes in the world sits underneath California, lying dormant for the past 100,000 years. Now, researchers have gotten a clearer glimpse into what lies below the Long Valley supervolcano, uncovering 240 cubic miles of magma sitting beneath California. It's important to start by saying this doesn't mean there is any imminent danger. Experts at the United States Geological Society, USGS, are actively monitoring the supervolcano, and while there has been an uptick in activity over the past 4 decades, there are no signs of an eruption. The Long Valley Caldera is the depression formed from the supervolcano eruption 760,000 years ago, which ejected hot ash, lava, and toxic gas. The eruption 760,000 years ago erupted 140 cubic miles of material from the supervolcano. To put this into perspective, the 1980 eruption of Mount St. Helens erupted 0.29 cubic miles of material, meaning the Long Valley eruption ejected nearly 500 times that amount of material. If all of the 240 cubic miles of magma found beneath the Long Valley supervolcano were ever to erupt, it would eject over 800 times the volume of material as the 1980 Mount St. Helens eruption. This is the reason geologists with the USGS continuously monitor the supervolcanoes that lie dormant beneath America. If and when one does erupt, it will trigger catastrophic destruction and loss of life. Fortunately, there is an extremely low likelihood of any supervolcano eruption occurring in any of our lifetimes. These eruptions happen very infrequently, but when they do happen, the world notices. Scientists began noting that the Long Valley caldera began growing around 1978 and has been doing so ever since. This gradual growth likely represents the influx of magma into the magma chamber below the supervolcano, essentially filling the tank in preparation for the next eruption. While the supervolcano has been studied for decades, it has been difficult to determine the amount of magma that lies beneath Long Valley. A recent study published in the journal Geology lays out new data in our understanding of the magma reservoir. Researchers from the U.S. Geological Survey's California Volcano Observatory in Menlo Park, California, were able to image a previously blind spot beneath the supervolcano. The team used seismic tomography to study and estimate the reservoir volume and degree of melt. To do this, geologists and geophysicists emitted strong waves from an array around the Long Valley caldera. As the waves traveled through the Earth, they would have bounced off rock differently, depending on the chemical makeup of the rock, whether it was liquid or solid, the angle, or other factors. They then measured the waves as they came back to the surface of the Earth. By using a supercomputer at NASA's Ames Research Center, the team was able to decode an image of the subsurface and map the reservoir of both solid and molten rock beneath the Long Valley supervolcano. The team found 240 cubic miles of semi-molten magma, with 27% in the liquid state. Now that we get the picture of what a supervolcano is, what makes Yellowstone the most dangerous of them all? Let us check out past eruptions to get a glimpse of what sets this force of nature apart. The Mesa Falls eruption. When people think of Yellowstone, they typically think of Yellowstone National Park, complete with its spectacular geysers and hot springs, abundant wildlife, and stunning volcanic features that attract millions of visitors each year. Volcanic features within the park largely reflect the recent geologic history of Yellowstone. Well, recent in a geologic sense, over the past 631,000 years. However, the beauty and outstanding geologic history of the Yellowstone Plateau volcanic field are not confined to Yellowstone National Park. Indeed, a stretch of U.S. Route 20 in Idaho between Ashton and Island Park, just west of Yellowstone National Park, provides a unique opportunity to view 2.1 million years of Yellowstone's volcanic history in an easy 30-minute drive. Mesa Falls is the second most recent caldera-forming eruption from the Yellowstone hotspot and ejected 280 kilometers of material. This eruption, 1.3 million years ago, was preceded by the Huckleberry Ridge Tuff and succeeded by the Lava Creek Tuff, both of which were also formed by the Yellowstone hotspot. If the Mesa Falls is the second eruption of Yellowstone, it begs the question, what was the third and crowning eruption? The Lava Creek Tuff eruption. The fallout from the eruption blanketed much of North America, depositing one of the most widespread airfall pyroclastic layers, formerly known as the Type O Perlet ash bed in the United States and Wascana Creek ash in Canada. The thick tuff formation resulting from this eruption is well exposed at various locations within Yellowstone National Park, including Tuff Cliff along the Gibbon River, Virginia Cascade, and along U.S. Highway 20. Lava Creek. Tuff ranges in color from light gray to pale red in some locales. The rock texture of the tuff ranges from fine-grained to aphanitic and is densely welded. The maximum thickness of the tuff layer is approximately 180 to 200 meters. Ash flows of the Lava Creek. Tuff are divided among 6 members, informally named Unit 1, Unit 2, Member A, and B from bottom to top, with Unit 3 and Unit 4 having unspecified stratigraphic positions. The emplacement of the lava creek tuff was not instantaneous and continuous. Rather, there were multiple pauses, and the members erupted at different times. Thanks for watching. Make sure to subscribe to our channel and check out another of our interesting videos.